Oh, so you have read and watched videos about how scientists found how what an atom is made up of. So Rutherford's scattering experiment. So up until now, we've talked about what an atom is made of. So we know there are in the nucleus there are neutrons and protons, and around the outside there are electrons. So actually, that's not quite the full picture. We've also got things that are even smaller than that in an atom. Protons and neutrons turns out that are made up of even smaller things. So Rutherford's idea of firing something at a target to discover its structure is known as scattering. So he used alpha particles since they were among the particles with the highest available energies at that time. However, over the years, scientists would develop and improve particle accelerators, which basically smash atoms together to see what's inside of them. Okay, so atom smashers to enable them to probe deeper and deeper into the fundamental structure of matter. These accelerators pushed back the bounds of technology, resulting in higher and higher energy. Nearly 200 new particles were discovered with exotic names like pions, muons, and neutrinos. And this is often known as the particle zoo because of the large numbers that were discovered, apparently with many different qualities and properties. So, as with the development of the periodic table, which you've read about already, these particles were grouped together by their properties to reveal the possibility of some kind of underlying structure. Experimental evidence to support this theory came in the 1950s when the scattering of high-energy electrons from nuclei by Robert Hofstadter, an American physicist, revealed some underlying patterns indicating that protons were not fundamental particles. So there was something inside protons making up protons. And he was a joint winner of the 1961 Nobel Prize of Physics for his pioneering studies of electron scattering in atomic nuclei and for his consequent discoveries concerning the structure of nucleons, so the structure of things inside the nucleus. This work did not conclusively identify the number and nature of the constituents of the protons, however. So he knew that there were things inside protons and inside neutrons, but he didn't really know what they were. And that happened in 1964 with Murray Gell-Mann and George Zweig, and they both independently proposed that protons and neutrons consisted of three smaller parts, and Gell-Mann named them quarks. And the particle zoo was reduced to a much more manageable number of fundamental particles, and all of those lots of different pions and things are made up of these fundamental quarks. And the Standard Model is basically a periodic table for those quarks and some other particles. So the Standard Model was developed to include these fundamental particles of matter and also to describe how they interact with each other. And Gell-Mann won the 1969 Nobel Prize for Physics for his work on the theory of elementary particles. So I believe you watched the videos as well. Antimatter. So every piece of matter has an antimatter. Okay, so antimatter is basically exactly the same as matter, except it's got the opposite charge. So high energy collisions also revealed the existence of antimatter. And antimatter consists of particles that are identical to their counterparts in every way apart from their charge. So an antiproton has the same mass as a proton but has a negative charge. An antielectron has a positive charge. You've briefly touched on that in nuclear physics. Every particle of matter has a corresponding antiparticle, and these were first proposed by Paul Dirac in 1928 when he noticed there were two solutions to the equations he was developing to describe electron interactions. The second solution to the equations was identical in every way apart from its charge, which was positive rather than negative. And this was named the positron, and experimental proof of its existence came in 1932 when they were discovered to be produced naturally from cosmic rays. And this is the only antiparticle with a special name. Every other antiparticle is just anti-whatever. So, annihilation. So annihilation occurs when you've got a particle and an antiparticle, and they meet and they basically smash together and they form energy. It just produces pure energy. So annihilation occurs when a particle meets its antiparticle and both the particles disappear. At low energies, this results in the production of a pair of photons, i.e. the combined mass and energy of the particles disappears and is replaced by pure energy. Conservation of energy and momentum mean that it's always at least a pair of photons that is produced. Photons you'll learn more about as you go through the course. Photons are basically particles of light. At higher energies, more than 2 photons and various other heavy particles may be produced. Many of the new particles discovered in the 20th century were identified by deliberate annihilation experiments. The top quark was one such particle, the existence of which confirmed at Stanford in 1992 in a collision of energy 176 giga-electron volts, which is a lot of energy. And antimatter is also created naturally in radioactive beta decay. We've talked a bit about beta decay already, but we're going to talk about it again. So the neutrino and the antineutrino, these are the things that are created in beta decay. So positive and negative beta decay create neutrinos and antineutrinos. So we already know that radioactive beta decay produces an electron, but how can a nucleus emit an electron when there are no electrons in the nucleus? So in beta decay, a neutron decays into a proton and an electron. So you've seen this in nuclear physics already. So we've got a neutron decaying into a proton, and then it fires off an electron as well. The electron is forced out at high speed due to the nuclear forces, and it carries away kinetic energy. Precise measurements of this energy have shown that there's a continuous spread of possible values. It's not just at one energy, it could be at a variety of different energies. So there's like an energy spectrum of that energy of the electron. And that was not expected, because when you've got alpha decay, alpha radiation comes out at a certain energy. We can predict what energy that alpha particle will come out at, depending on the reaction. But we couldn't predict what energy the electron will come out, because it could be a number of different energies because of this spectrum. So, for example, protactinium-231 emits alpha particles with 9 distinct energies, so it could be one of those 9, but only one of those 9. These separate energies can be calculated from the difference in the energy of the emitting nucleus before and after the decay process. But the electrons in beta decay come out with a range of energies up to, but not included, the expected value. So something else was needed to account for that missing energy that we actually expected it to come out by doing calculations. And the thing that we discovered that made up for that extra energy were these neutrinos or antineutrinos. So beta negative decay, remember, is a neutron changing into a proton plus an electron plus an antineutrino. Okay, so Pauli proposed in 1931 there must be another particle emitted in the decay. Since this had not been detected, it would have to be neutral and highly penetrating, meaning it didn't interact with the detectors. It was later named as a neutrino, but we now know it's an antineutrino, and that's in beta negative decay. Beta positive decay, there's a little misprint in your booklet, so just make sure you change that. Beta positive decay is when a proton changes into a neutron and it gives out an anti-electron. We know that there's a name for that, it's positron, and a neutrino, so not an antineutrino. So in beta negative decay, it's a neutron changing into a proton, giving out a normal negative electron and an antineutrino. In beta positive decay, it's a proton changing into a neutron, giving out a positive electron, an anti-electron, and a neutrino. So the top here is an example of beta negative decay, and this one is an example of beta positive decay. So the other type of beta decay, beta positive, has a certain symmetry with beta negative. In this process, a proton decays into a neutron, and a positron and a neutrino are emitted. So that's why I've basically got rid of that. That shouldn't be an antineutrino. Just a bit of information, more than 50 trillion solar neutrinos pass through an average human body every second while having no measurable effect. They are so penetrating that to detect them requires massive tanks of water solution and photon multipliers to detect light produced by an interaction with the chemicals in the solution. These tanks are usually buried deep underground to prevent interference from other particles. And Pauli originally suggested the neutrino be called a neutron, but obviously we know neutrons are a different particle completely. So the particle we now call the neutron would not be discovered for another year, and Chadwick seemed unaware of Harvey's suggestion. Fermi suggested the name neutrino, which is Italian for small neutral one, to distinguish between the two. Okay, I'm going to pause there, and then we'll move on to this booklet a little bit more and actually read about the Standard Model, this sort of periodic table for